Taking derivatives of piecewise functions, we have to understand piecewise functions as opposed to piecewise functions, which would be how did Gandhi operate or whatever. But so one of the best ways to understand a piecewise function is to build one. Let's suppose I want to build an amusement park for my ants. I got an ant farm and I could charge them for the roller coaster. It'd be awesome. I could make some dough. So anyways, let's suppose I'm going to make a roller coaster. I don't know, maybe there's like 13, what would they be? Decimeters long or something like that for my little ants. Well, they'd be riding up the thing, get to the top and go whee, and then come off, and we'd have to let them down easy. So what I have to do is model this then using three different functions, three pieces to the function right here. Well, first we'd be going up a line and it's pretty much straight up. So we'd say, well, this part of the function would just be y is equal to x. And so it started at 0, ended up at 5, so this would take us up 5 units high. We'd be 5 units high, we have to go down a parabola that hits the x-axis at 8, and there would be a double root there. So remember what that means. If you have a parabola with a double root somewhere, to shift it over 8 units to the right, we'd have to have this, and it is a double root. So if we did that, that would be a parabola that would go over here and do that. Yeah. Now, what about this? Though at 5, when x is 5, we have to have it be 5 units high. Normally, if you put 5 in here, 5 minus 8 is negative 3. Square that, you get 9, and we're only at 5. So we'd have to make this guy 5/9. So there we go. That would be our middle piece to the function. And then up here, once we got to 10, we'd have to let the ants down easy on a line again. So then we'd think about, okay, now at 10, where would the parabola drop them off on the roller coaster? Well, 10 minus 8 is 2, 2 squared is 4, 4 times 5 is 29. So these guys would be up here at a height of 29ths. Now, we're going to have to take them from 29ths down to 0 over the course of 3 decimeters. So we're going to have to divide 29ths by 3, and that would give us 20 27ths. And we got to go in a negative fashion like that, so that would be the slope of this line, and that would take them down to the ground. Now, what we'd have to do is figure out, well, at 10 units for x, we're up here at 29ths, so we're going to have this same slope going back 10 units. Every time we go back 1 unit, we go up 20 27ths more, so 10 of those would be up 227ths. So we'd have to start at 227ths to come down to here, and then we'd have to end up in here, so we have to add 29ths, which is really 60 27ths. So this would be 260 27ths minus that. So that would be the third piece to our function. So all we have to do is say, all right, then we have a piecewise function that would make this roller coaster, and we would say that this function was f of x. Now the first part of the roller coaster, which would be between 0 and 5 seconds, would be the line. So this would be the line y equals x. So f of x would just equal x. And then we'd have to have this parabola for the next part, so it would be 5/9 x minus 8 squared, and this would go from 5 to 10. So this would be from 5 being less than x, being less than or equal to 10 decimeters, and the last part would be this guy, and if we put it in mx plus b form, it would be this slope, and then plus the 260 27ths, and this would be when x was greater than 10. So there it is. There's our piecewise function that models this little roller coaster we put together for our ants. So okay, so we can understand that a little bit. That's how a piecewise function works. We have different parts of the x-axis describing what portion of those functions that we're going to use. Okay, now if we were to take the derivative of this piecewise function, all we have to do is take the derivative of each part. The derivative of this part here would just be 1. So the derivative on this part would equal 1, which makes sense because the first derivative is the slope of the tangent line. Well, the slope, no matter where we go, is going to be 1. So that makes sense that we'd have that. Then we take the derivative of this guy. Ooh, that means we bring the 2 in front, making that 10 ninths times x minus 8 to the first power, and then we multiply with it. Oh, okay. So we would just have that the derivative here, f of x, would be, what did we say, 10 ninths times x minus 8. So, depending on where we were on this part of the roller coaster, this would define how steep we'd be falling or rising at that point. So at 6 seconds, we could put a 6 in here. 6 minus 8 is -2, times this would be -29ths. So we're coming down on an angle of -29 decimeters per decimeter that we run in the x direction. So we'd have that. And then we go down here, this last part, this has a negative slope to it. If we take the derivative of this guy, it's a linear function. The derivative of this is just going to be -20/27, no matter where we are. So no matter where we are on the x, on that interval for x, the slope of that part of the function would be -20/27. So that's it. That's piecewise functions. You just take the derivative of each piece and then use it to do whatever you want to do with that. Okay, then finally, let's build another one here. Let's look at another roller coaster. We got a piecewise function. We haven't built it, somebody else did. Let's see what this bad boy looks like. So what we have here is, first we have this part, 3x plus 50. So that's a y-intercept of 50 with a slope of 3x, and it comes from below 0. So we're going to have something coming from down here, and it's going to end up hitting here at 50. And then we hop off of this guy just prior to 50, so open circle there. Then we hop on this parabola, and this parabola would go down this way, and all right, so this guy would go down here and do something like this right here. And all right, so we'd have that piece to it as well. So if we wanted to find a formula for the derivative of this, if we took the derivative of this, the derivative of this guy would be 3. That means the slope is 3. Now the derivative of this would be that we would get 4x minus 20. So that would give us a formula for the slope. And as soon as we got here to 5, where there would actually be a double root, then the slope would be 0, because that's the min. It's supposed to be hitting on the x-axis, pretend it is. And then so positive slopes after that, negative slopes prior to that. Now the other thing we have to be careful about is, when you have a piecewise function, we get these cusps, or these corners here. And even though 0 is part of our domain, we're saying that we could be on this parabola at 0. The problem is the way that this guy connects then to this other one, we have no derivative. Their first derivative would not exist at 0. So the derivative of this function does not exist when x equals 0, and it's because it does not exist. I shouldn't say not equal to, it just does not exist. Because if you think about it, a first derivative is supposed to give you a slope. And so if you, the slope of the tangent line, and hopefully we realize that there would be infinitely many lines that could be tangent to that point. You could have a line going this way, a line going that way. The lines could go in many different directions. So when you have a corner on a graph, first derivative doesn't exist there. So just keep that in mind when you're dealing with piecewise functions. And then finally, if you have an absolute value, don't forget what this means. The parent function, f of x, equals the absolute value of x, is that v thing that's with the vertex at the origin. And again, the first derivative would not exist right at 0, because there's a corner point there. But then remember what happens if you substitute in for x, this quantity, x plus 7, what that does is it actually shifts that parent function 7 units to the left, because the lowest value for y right now is going to occur at -7. You'll get a 0 there. So that's why this function is moved this way. So now the way to find the derivative of this is to say, well, you know what? I need to split it up into 2 pieces. So we can take this function here and we can recognize where the corner is, and so we build a piecewise function to say that if this quantity is positive, and it's going to be a positive quantity as long as you're above the -7, then we don't even need the absolute value signs. So for x greater than -7, we would get this part would be this part of this graph. And then this guy over here would have a negative slope. It would be the opposite of this. So if you think about it, if this was a negative quantity, we could change that into a positive quantity by taking negative of that negative value. So that would give us a line that would look like this, where the y-intercept would be down at -7. And I should have done that with a different color. So let's make that -x minus 7. That would be the piece of the graph that would be below -7. So that would be this guy right here. So once you take the absolute value function and split it into two pieces, when you take the first derivative of this, you get 1 because the slope is 1. Boop. When you take the first derivative of this piece, you get -1 because the slope is -1. So that's how we can deal with piecewise functions and then use the piecewise to allow us to do a better job analyzing what happens with absolute value functions.